Okay, so today we're going to basically cover two topics. So I'm going to finish talking about air pollution. We just have a few slides left, basically talking about the evidence on long-term air pollution exposure, how that affects people's health. I might talk a little bit about a current study that I'm doing as well that's related to that. And then the second thing we'll do is talk about evidence on fracking in health, which is hydraulic fracturing. We'll talk about what that is, why it potentially could cause water pollution, and go over a recent study that it's not even been published yet, still a working paper. The publication lag times in economics are very, very long, so often research gets circulated as a working paper, and people already kind of know all about the results and stuff like several years before it actually comes out in print in a journal. But I'm sure in a couple years this paper will be printed somewhere. So that'll be sort of the second half of the class, and my guess is we'll finish that, and we'll continue talking about it on Friday. In terms of the midterm, so I'm going to post solutions this afternoon, which you can look at if you want, but certainly you shouldn't feel any obligation to look at them. In particular, so these are the solutions are like the idealized answer, but just because you didn't give that exact answer doesn't mean you won't get most of the credit for the question, or in some cases all of the credit for the question. So just because you see something that looks maybe somewhat different than what you wrote, don't necessarily freak out. In terms of the grading, my guess is we'll have it graded sometime next week, but I can't give a forecast to say exactly when. Also, so when I post the solutions, as you could almost certainly infer during the exam, there are two versions of them, so you should look at these solutions for your version. I guess you won't necessarily know which version, but the main difference is on the second question. So if you had the version where there was like a cost function that had 500 in it, then you have version A, and if you had the version where the cost function had 400 or any type of 1100, then it was version B, and the answers between the two versions are significantly different. So don't look at the wrong version and think you did the wrong thing. Okay. So in terms of air pollution, so the last thing that I want to talk about is basically what evidence we have about the effects of long-term exposure to air pollution on mortality rates. So the problem with thinking about long-term exposure is that we can't find by definition, we can't use like high frequency or short-term variation in air pollution levels to estimate the effects of long-term exposure because it's a long-term thing. So all of the evidence pretty much to date relies on what we call cross-sectional correlations, which are just looking at how people in one area, like what mortality rate of people in one area is relative to the mortality rate of people in another area when those two areas have different levels of air pollution. So the most famous study in this literature, which is more by like epidemiologists and medical people, is what's known as the 6 Cities study. As you might imagine, it follows people in 6 cities. In particular, they had data on 8,000 adults who lived in these 6 cities for about 15 years. And so what they do is essentially look at the correlation between mortality rates across cities and pollution rates across cities. So it turns out there's significant differences in the pollution levels across these 6 cities. And then, so they look at the raw correlation, and then they also think about basically running a regression where they regress mortality rates on pollutant levels at the city level, and then also control for whatever observable characteristics that they have about these individuals. So they have things like the people's age, their gender, smoking habits, education, body mass index. And so after they control for these things, they find that adults that were living in the most polluted city were 26% more likely to die during the 15-year period that they were following them than adults living in the least polluted city. So, on the one hand, so if we just think about like the raw correlations, I think the relationship is probably stronger if they don't control for any of these variables. If you just think about that raw correlation, you'll probably not believe that at least all of it like represents a causal effect, because you could certainly think that people who live in the most polluted city are probably sort of different along a number of dimensions than people who live in the least polluted city, and those dimensions might have impacts on mortality. So they do control for things that will be important, like age and whether or not you're a smoker and body mass index. Those things are all clearly going to have predictive effects on mortality rates, and could potentially also vary across the cities in a way that's correlated with pollution levels. So they control for that stuff, and they do still find an effect. But I think it would be wise to sort of be skeptical and think that there could be other unobservable characteristics that they don't have in their data that are correlated with pollution levels and have some relationship with mortality. So there could still be some limited variables bias here. So in terms of like just looking visually at what they find, I think this is kind of like the most convincing part of the paper. It's not to say that the paper is like super convincing, but the relationship visually does seem like it's pretty strong here. So what they have here are basically measures of particulate pollution on the x-axis. So either total particles here or just fine particles. So basically total particles. Basically what that means is like they're looking at the concentration of coarse particles, like larger particles. The reason is that those larger particles will dominate the total mass of particles. So these are like micrograms per meter cubed, and so it's a measure of the mass of particles per cubic meter of air. So the size of the particles are really going to dominate, or the larger particles are really going to dominate that total mass. And then they also look at the measure of fine particles per meter cubed of air, so that's like you filter out all of the larger particles and instead look at the fine particles. The sort of medical literature, I think, tends to think that the finer particles are potentially worse for health than the coarser particles, just because they can sort of infiltrate into your lungs and potentially into your cardiovascular system more easily than the coarser particles. So what they're doing here is each of these letters represents like a city. So remember, there's 6 cities, so there's 6 letters there. And so what you're looking at are just the basically like the mortality rates that are that's actually like the mortality rate normalized against the lowest mortality city or the lowest pollution city. The two are the same in this case. So you have this normalized mortality rate by city being plotted against the average pollution level by city. And so you can see that the main result of the paper here is that as you go up in terms of pollution levels, mortality rates also seem to rise. And it's not a monotonic relationship. It's not always the case that a higher pollution level city has a higher mortality rate, but it generally is the case. And certainly the highest pollution level city, which is like Steubenville or something like that, the S, that one clearly also has the highest mortality rate. So for particulate matters, for particulate pollution, there's certainly a relationship there. Again, how much of that relationship represents a causal effect versus potentially just being a proxy for like other variables that we can't observe that might have an effect on mortality rates. It's hard to say. So sulfur dioxide. So they have a bunch of different pollutant measures for these cities. So that was the first one was particulate matter. That one turns out to be like the most predictive or the most strongly correlated with mortality rates. They also look at sulfur dioxide, sulfate particles. Seems like there's some relationship there as well. Ozone though is sort of less strongly correlated with mortality rates. So particularly when you're looking at the furthest right graph there, the ozone parts per billion. It's hard to say whether there's any relationship there at all. Technically, if you fit a line through those 6 points, it would actually have a negative slope instead of a positive slope, but I doubt that it would be statistically significant. So despite that evidence, it's hard to say whether the correlations represent causal effects. You can certainly imagine that there are many unobservable characteristics about these people that could affect mortality rates and be correlated with pollution levels across cities. And so it's hard to rule out the possibility of confounding or omitted variables bias, even when they're controlling for those observed characteristics. There was a follow-up study later on that they did, which was like, I don't know, the 100-city study or something. They increased the sample size considerably from 6 cities to somewhere around 100. They found pretty much similar results. So like the slope of the relationship was like a little bit less wrong, but the statistical significance went up just because you have a much larger data set. So that did kind of replicate the original results. But again, any sort of like omitted variables bias type story that you could tell in a 6-city study, you could also tell for the 100-city study. So let me actually just sort of briefly describe a couple of more recent papers. Well, one more recent paper and then one paper that I'm currently doing. So there was a study like last year by Michael Greenstone, who was the guy that was involved in the speed limits study. And so it was, he calls it the like Huai River study, but it's basically using a river in China that, it's not actually using a river, but it's using like approximately where the river is as a discontinuity in pollution level. So there's this policy in China that if you're above a certain latitude that's approximated by where this river is, then you qualify for free heating because it's colder. And then if you're below that latitude, you don't qualify for free heating. And the way that the heating is provided is not like, it's not like here where most of our heating is natural gas, where you're actually burning the gas inside your apartment or inside your house, but rather it's provided via like a centralized coal burning plant. So there's like a plant that serves entire neighborhoods basically. And so it'll burn coal, which is a very dirty fuel, especially because it's probably a relatively old plant. And then it pipes out like hot water to the houses that then use it as to power like steam radiator type things. And so it turns out that the provision of heat is actually a major source of pollution for the cities that lie above the river because it's so dirty. So essentially, what you do is, or what the main result in the paper is making a figure where you have latitude on the x-axis, and then on the y-axis you have either the pollution level, which is going to be in terms of like particulate matter, or I'll make like a second y-axis over here, which would be like life expectancy, the mortality rate. And then so you're going from like basically the south here to the north as you go to the right on this figure because latitude is increasing. And so when you get to like the boundary where you switch from basically the no heat regime to the free heat regime. So this is really, switching from a case where you don't have these big centralized coal burning plants to a case where you do have these big centralized coal burning plants. You certainly see what you expect in terms of pollution levels. So basically, it's like the average pollution level it's like increasing, and then it jumps up considerably once you cross that boundary and go above the point at which you have these big coal burning plants. So the idea is that the notion here is that you could use this change in pollution levels to try to see whether or not there's like a parallel change in mortality rates. And in particular, so if you like, the idea here is really that what you would like to do is kind of like try to focus on this region where you're kind of near the dividing line. And so the justification is that if you were to compare a city that's over here to a city that's over here, so you're comparing like a city that's really far to the south, which would be like Hong Kong, I guess, and comparing that to a city that would be really far to the north, which would be north of Beijing. Those two cities are very different. They have completely different climates. They're going to have like sort of different ethnic makeups. They're going to have different sort of industrial bases and types of employment that people are types of jobs that people are employed in and so forth. And so you can imagine that even if you observe different mortality rates comparing the extreme northern city to the extreme southern city, some of that might be due to differences in air pollution, but there also could just be a lot of different things about those two types of cities, right? So instead, what you want to do ideally is sort of compare cities that are pretty close in latitude and maybe ideally in longitude as well, so that you're comparing cities that look pretty similar, but that have potentially different pollution rates, right? So that's going to be like a much better sort of treated and controlled type comparison than considering an extreme southern city and comparing that to like an extreme northern city. Now, the issue here, of course, is that like you can't go too close because the pollution itself doesn't respect the boundary of the river. So if you went very close to where the river was, then even though you might not have a coal plant in your specific city, you could have pollution that was drifting from the city that's up to the north. But this is really, this is like you're talking 1,000 miles or more in terms of the difference here between the extreme south and the extreme north. So you have plenty of room to work with here. So they do show that there is an increase in pollution levels when you cross this boundary, and they also show that there does seem to be some increase in mortality. So this is like a little bit weaker, but kind of like mortality rates. This is like particulate matter, PM, and then I guess I said life expectancy. So basically, it's like life expectancy does seem to kind of change here, although it's really not as stark as the change in pollution. So the bottom line is when they actually like calculate out the numbers, I think they get like sort of a several year drop in life expectancy. They forecast like there's a several year drop in life expectancy when you cross that dividing line, switching from like no heat to free heat. And if you kind of then project that all the way to the north and say like every city that's north of this north of this boundary is experiencing sort of a several year drop in life expectancy relative to what they would have if they either didn't have the coal plant at all or if it were just like a much cleaner plant, then the total sort of potential externality from all of that pollution works out to some huge number, like $1 trillion. And because China has so many people, and like a 5-year change in life expectancy is like very significant. I mean, you have to sort of go back at least a couple decades to see like an overall increase in life expectancy of at least 5 years in the U.S., even though life expectancy does continue to sort of rise on average every single year. So the number, the potential externality here is really big, but at the same time, the estimates, like when you actually look at the figures, not sort of clean as I've drawn it up here. So the estimates aren't quite as robust as you might hope. So the other thing, the other like study that I'll talk about for a few minutes is one that I'm doing myself right now, which hopefully, I already have a draft and hopefully it'll be like a finalized draft by the end of the semester. But what I'm doing is essentially looking at basically like looking at mortality rates of households in Los Angeles who live close to highways. So the idea here is that so if you think about So if you think about like a highway, so this is a little bit similar to like that Easy Pass paper that we talked about before, but different. So if you think about a highway, it turns out that as you would expect, in general, there are like elevated levels of pollutants, particularly ultrafine particles, near highways because of all the all the traffic. So that's been established in the atmospheric sciences literature. And then it's also the case that which side of the highway you're on actually determines sort of what dose of pollution you get, right? So if you can imagine that if you're in an area where the winds tend to blow in one direction, so for example, if they blow from like west to east here, then people who are living like downwind of the highway on this side are going to end up getting a significantly higher dosage of pollution than people who live upwind of the highway on this side. So you could think of potentially like considering these people who are pretty close to the highway on the downwind side as being kind of like treated with a higher dose of pollution, and the people who live on the upwind side as being essentially like controlled individuals who are exposed to less pollution. So the reason that you want to ideally, like the reason that you kind of need this control group is that if you just consider these treated people who live within say 1,000 meters of the highway and compare them to like the general population of Los Angeles, what you would find is that they look different on average in terms of their observable characteristics, the things we can see about them, like race and age and so forth, and potentially like income levels and so forth. So they look different than the average person in Los Angeles, which is where the data from the study are coming, because as you can imagine, like living next to a highway is not really generally considered to be a desirable location, and so typically you'll find sort of like lower priced and like worse quality housing stock right near the highway relative to sort of an average neighborhood that's not close to the highway. So you don't really want to do a comparison where you're comparing people who are right next to the highway to people who live in the suburbs or something like that. Instead, ideally, what you'd like to do is find another group who also live right next to the highway but aren't exposed to air pollution. So that's where essentially the winds come in. So because there are like pretty consistent wind patterns, you can use these people who are upwind of the highway as like a control group for those who are downwind of the highway. Now the advantage here is that you can imagine that as long as like sort of moving rates aren't too high, so as long as people are living in the same houses for a substantial period of time, then what you have is not just like a difference in exposure to pollution, but you actually have like a difference in sort of relatively lengthy, like I don't know if you want to use the term long term because that could have sort of different interpretations. So I mean, I can't claim that people who live here have necessarily been exposed to high pollution levels for all their life because it's unlikely you'd end up living in the same house for all of your life. But I can show that on average people who have been living here have been living for maybe 5 to 10 years. So it is a multi-year sort of difference in exposure to pollutants. And but then the question is, do we actually see higher mortality rates on the downwind side relative to the upwind side? So to answer that question, turns out that there's like California actually, so we have a census of deaths, and there is something called a death address file where you actually know the address of every single person who died over several years. So you can link that to census block information and calculate basically the death rate for various different age groups by census block. Census blocks are about the size of a city block in a place like San Francisco or in Los Angeles. So these are sort of very precise data in terms of like the geocoding aspect. And so when you do that and then calculate the death rates, what you find is what you would probably expect if you thought that there was a negative impact of air pollution. So there are groups that seem to be affected, in particular like sort of the elderly, so people who are certainly people above 60, and in particular people who are like above 75. For those groups, I do find a substantially higher death rate for people in that age group who are living downwind of the highway versus upwind. If you just look at sort of everybody, or say everybody over the age of 40 or something like that, you don't find any significant difference, which is probably consistent with what you would expect or hope, because those people, just mortality rates for that group tend to be very low, especially mortality rates for sort of non-accident related causes. And so you wouldn't tend to think that those people would be too badly affected by air pollution. Although I suppose it could, there could be some sort of compounding effect over time, where once they become 70, then it's bad news. But at least at the in their 40s and 50s, it doesn't seem like there's any effect. So that's sort of where that is right now, and hopefully it'll be done by the next time I use this class. Did you have a question? Okay, so that's it for air pollution. So then the next thing that I want to talk about, which is actually a relatively new addition here, is fracking health. So this is, when people say fracking, what they're referring to is something that's called hydraulic fracturing. This is something that the technique itself has sort of been around for several decades, like it's been known, but it hasn't really become popular until pretty recently, like in the last decade or so. And so the reason for that is essentially that as energy prices increase, you have an additional, you have increased incentives to try to get at reserves of natural gas and of oil that previously were not considered to be like economically feasible to develop, but at a certain price level, pretty much anything can become economically feasible to develop. So even if it turned out that if there was like some resource where, I guess there were like some resource where you had to fly to the moon to get it, that would not be economically feasible to develop right now. But in theory, if the price were like $1 billion per gallon of gasoline or something like that, and you knew that there was gasoline or crude oil on the moon that you could get and bring back, then it would at some point become economically feasible. So, although not in that case, because I'm sure it would take more kerosene to actually get to the moon than you'd ever be able to bring back. So the less extreme case here is, we're talking about oil going from maybe like $30 or $40 a barrel to around $100 a barrel today. Natural gas is a little bit different. I think it was going up for a while. Now the prices have actually come down somewhat. I think in part because they have been so successful in developing these previously undeveloped, also like unconventional reserves of natural gas. So the actual technique itself is what's referred to as, well, so it's called fracking, but the full name is horizontal hydraulic fracturing. And what it does is it basically allows you to get natural gas or oil out of these shale rock formations that are well below the surface of the ground level that have a relatively low density of hydrocarbons. So these are like formations that previously didn't look very attractive because there's not a high density of the gas in it. You have to drill deep down to get it, and you have to not only sort of drill down vertically, but then you actually have to go horizontally because they have a relatively low density. So if you just drill down vertically and try to get whatever you could get from there, you wouldn't get all that much. So not only do you have to drill down and then start going horizontally, but you also have to do something to basically encourage the hydrocarbons that you want to